Hello viewers, in today's class we are going to discuss yet another important application of Lagrange's mean value theorem to prove this inequality, right? So here we have to prove this inequality where we have log of 1 plus x is less than x plus 2x square over 1 plus x for all x greater than 0, right? So let us start, right? See, in Lagrange's mean value theorem, what we usually do, we first define an appropriate function in some interval, right? So here we'll define a function y is equal to f of x is equal to a log of 1 plus x minus 1 over 1 plus x, right? So here we'll define this function and we'll see whether this function satisfies all the conditions of Lagrange's mean value theorem in the interval 0 comma x where x is greater than 0, right? So the Lagrange's mean value theorem, the first condition is that this function f of x it has to be continuous, right? So here we see that this function f of x is the difference of these two functions, right? So the first function is the log function and the second function is the rational function, right? And for all x greater than 0 or in the interval 0 comma x, this function is a continuous function. So fx is a continuous function in the interval 0 comma x for all x greater than 0. Why? Because see, this log function is continuous, right? This function is continuous in the interval 0 comma x, and this function, that is 1 over 1 plus x, is also a continuous function in the interval 0 comma x, right? So if we take this function as h of x and this function as g of x, then f of x is the sum of two functions, right? We can also take this function g of x as negative of 1 over 1 plus x. So f of x can be represented as h of x plus g of x, right? So h of x is continuous, g of x is continuous, and f of x is the sum of two continuous functions, right? So f of x is also a continuous function in the closed interval 0 comma x for all x greater than 0, right? So now the second condition of Lagrange's mean value theorem is that this function f of x has to be differentiable in the interval 0 comma x. So fx is differentiable in the interval 0 comma x for all x greater than 0, right? Why? Because if we find the derivative of f of x with respect to x, then what we will get? See, the derivative of log of 1 plus x is 1 over 1 plus x, and then the derivative of 1 over 1 plus x is a negative of 1 over 1 plus x whole square, right? And this is 1 over 1 plus x, then minus minus, when we multiply these two negative signs we'll get plus, so we have 1 over 1 plus x whole square, right? So f prime of x is 1 over 1 plus x plus 1 over 1 plus x whole square, and this expression exists for all x greater than 0 in the interval 0 comma x, right? So the derivative of f of x, it exists in the open interval 0 comma x, right? So the two conditions of Lagrange's mean value theorem are satisfied. So Lagrange's mean value theorem says that then we have a point C which belongs to this interval 0 comma x, or we can write C is greater than 0 and less than x, such that f prime of C must be equal to f of b minus f of a divided by b minus a, right? So there must exist a point x is equal to c between 0 and x once the function is continuous and differentiable, right? So we must have this expression. So here we have the interval a comma b. This is the usual notation. So a is 0 and b is x, right? So f prime of c is equal to f of x minus f of 0 divided by x minus 0, that is f of x minus f of 0 divided by x, right? So now f prime of c can be obtained from this expression, right? From this expression. So here we'll take x is equal to c. So we have 1 over 1 plus c plus 1 over 1 plus c whole square, and this is equal to f of x. So f of x is log of 1 plus x. Then we have minus 1 over 1 plus x. Then we have f of 0, right? So here we can find out separately the value of f of 0. So f of 0 is log of 1 plus 0 minus 1 over 1 plus 0 by taking x is equal to 0 in f of x. So we have log of 1 minus 1 over 1, log of 1 is 0, and here we have 1, so this is minus 1, right? So here we can write minus 1 divided by x, right? Okay. So here we'll have minus of minus 1, right? Because f of 0 was minus 1, so we have here minus 1, right? Okay, so now we can write it as log of 1 plus x minus 1 over 1 plus x, and this is minus plus, and we have here x, right? So now we have this expression, right? Okay, now we'll use this expression to arrive at this inequality, right? So how? See, here we have c is lying between 0 and x is greater than 0, right? So the term 1 plus c is obviously greater than 1 because c is greater than 0 and c is a positive quantity. So when we add c to 1, then obviously 1 plus c is greater than 1, right? So 1 plus c is greater than 1. So let us take the square of both sides. So we have 1 plus c square should also be greater than 1 square, which is equal to 1, right? Now let us take the reciprocal of both sides. So we'll get 1 over 1 plus c square is less than 1, right? Because once we take the reciprocal of both sides, then the direction of the inequality get reversed, right? Okay, so now we have this inequality 1 over 1 plus c square is less than 1. So we have obtained this term, right? So now what we will do in the next step, we'll add 1 over 1 plus c to the both sides of this inequality, right? So what we will get, we'll get 1 over 1 plus c plus 1 over 1 plus c square is less than 1 plus 1 over 1 plus c, right? So now this term 1 over 1 plus c plus 1 over 1 plus c square is equal to this term, right? So we'll replace this term by this term. So we have log of 1 plus x minus 1 over 1 plus x plus 1 divided by x is less than 1 plus 1 over 1 plus c, right? So now let us take this as inequality number 3, right? Okay, now to move further, what we will do, we'll take help of this inequality, right? See here, 1 plus c is greater than 1, right? So 1 plus c is greater than 1. So if we take the reciprocal of both sides, we'll get 1 over 1 plus c is less than 1, right? So the direction of the inequality get reversed, and now we'll add both sides 1, right? Because here we have 1 plus 1 over 1 plus c, right? So what we will get, adding 1 to both sides, we get 1 over 1 plus c is less than 1 plus 1. So this is 1 plus 1 over 1 plus c is less than 2, right? So this is inequality number 4, right? So now what we will do, we'll merge these two inequalities, right? That is inequality number 3 and inequality number 4. See here, 1 plus 1 over 1 plus c is less than 2, right? And here 1 plus 1 over 1 plus c is greater than this term, right? So if we now merge inequality number 3 and 4, then we'll get log of 1 plus x minus 1 over 1 plus x plus 1 over x is less than 1 plus 1 over 1 plus c, and this term is further less than 2, right? So here we'll write 2, right? And now we'll take this term and this term, that is the log of 1 plus x minus 1 over 1 plus x plus 1 over x is less than 2, right? So now we can rewrite this inequality over here. So we have log of 1 plus x minus 1 over 1 plus x plus 1 divided by x is less than 2, right? And see here x is greater than 0, right? So when x is greater than 0, we can safely multiply both sides by x. So here x get cancelled, so we are left with log of 1 plus x minus 1 over 1 plus x plus 1, and this is less than 2x, right? Now we can take these two terms to the right hand side of this inequality. So we'll have log of 1 plus x, then we have less than 2x plus 1 over 1 plus x minus 1, right? Now we can simplify the right hand side. So here if we take the LCM 1 plus x, then here we'll have 2x 1 plus x, then here we'll have 1, then here we'll have minus of 1 plus x, right? So log of 1 plus x is less than 2x plus 2x square plus 1 minus x divided by 1 plus x, right? So now let us simplify this inequality. So we have log of 1 plus x, and then we have 2x minus x is x, and this one get cancelled, and we are left with 2x square divided by 1 plus x, right? And this is our desired inequality, right? So we have log of 1 plus x is less than x plus 2x square over 1 plus x for all x greater than 0, right? So viewers, this is how by applying Lagrange's mean value theorem we can prove these type of inequalities.